Hey everyone, how's it going? I'm Dan Laine. I'm a software engineer at Ava Labs. This is about the crowd that I expected for a talk about using a database for syncing, so I'm very glad that I had some people at least. And this is a pretty small crowd, so I think it's small enough that if you have a question, you can just try to get one of their attention and they'll bring over a microphone, because it's pretty short talk, and I'm going to go over some things at a pretty high level, but depending on what questions you all have, I can kind of tailor it for that. So with that said, we're going to be talking about how you can use Merkle Radix Trie to make a database and do syncing with it. So I guess just so I have a better sense of the audience, who here is a developer? Okay, solid. Who here knows what a Merkle tree is? Okay, so pretty technical crowd. So I'll start with kind of some setup for like what it is we're trying to solve for here. So this is a pretty old problem in just the history of distributed systems. Is if you're a participant in this distributed system, you need some way to find out the current state of the network, the current state of the application that you're working with. And if you're in a Byzantine environment, meaning an environment where you expect there to be potentially adversaries who want to do malicious things, lie to you, convince you of things that aren't true, et cetera, or just mess with you, how do you actually download the state of the application that you're trying to run? So for the sake of this, let's assume that you can get some trusted hash or fingerprint of the thing that you're trying to download, which is a pretty reasonable assumption. The way that you would do this in a blockchain network is you query like every validator, let's say, or you query some subset of validators. And if, let's say, 90% of them agree when they report the hash of the database to you, then you can have a fairly high degree of confidence that that actually is the hash of the database, assuming that 90% of validators are honest. Or, let's say, not many are dishonest. So one thing that you could do, and this doesn't really work in a Byzantine environment at all, but you could just download the entire database from one of the existing peers in this distributed system, right? So you're like, hey, can I please have this database? And they say, sure, and they just send you every single key value pair in the database. And then at the end, you take all the stuff that they gave you, you put it together, you hash it, and you check if the hash that you got equals the expected hash. If you're in a centralized system where you are running all of the clients, then sure, this is fine. Like one of your clients isn't going to lie to your other client. If you're in a Byzantine environment, though, this is a terrible idea because someone could just lie to you, right? You're like, hey, can I please download the database? And this other person is trying to mess with you, and they just give you a bunch of garbage, and they just keep feeding you garbage, and then eventually you finish downloading it, and you hash it, and you find out, well, all of that was completely wrong, or at least some of it was wrong, okay? So did that make sense for this first algorithm for naively syncing a database? Cool. Okay, so a slightly smarter thing that you could do, and this is vaguely how torrenting works. You download the database. Okay, sorry, this is not the thing that I thought that I put next. So another thing that you could do is for every key value pair that you get when you're downloading the database, you basically do like a sanity check with everybody else in the network. And so if someone gives you like key 1 maps to value 1, you ask a bunch of people, hey, is this actually in the database? And then they'll tell you like, yeah, it is, or no, it's not. And then you can get a sanity check and make sure that you're getting actual valid values. As you can probably tell intuitively, this is a ton of overhead. So this is also not a super great idea. This one is how torrenting works. So basically, you take the database, you split it into chunks, and then you learn the hash of each chunk, rather than in the first one where we got the hash of the entire database. And then after you download a chunk, you hash it, you confirm that it's the expected hash, and then you go from there. This has a bunch of overhead, and also doesn't work so well if the database is changing all the time, because then the different chunk hashes are changing, and you have to learn about those, et cetera, et cetera. Oh, that's not good. How do I? So you guys saw none of the slides. Oh, all right. Well, hopefully I did a reasonable enough job explaining that you didn't need that. Okay, well, I'll just go back. Okay, approach 1, download entire thing, hash it at the end. Bad idea in a Byzantine environment. Idea 2, similar to 1, except sanity check every key value pair. Way too much overhead. Approach 3, basically what torrenting does, hash each chunk. And now I'm going to get into the discussion of the thing that we're actually talking about today, which is a Merkle Radix Trie database. So some of you might already be familiar with this data structure called a Radix Trie, also sometimes called Patricia Tries, which is, I think, a specific subset of Radix Tries. But basically the way that it works is this is a tree where every node in the tree's key is its path, right? So like you can see the cursor. Okay, so this node's key is T because it is the T child of its parent, and then its child is O. So this is 2, this is T, and I think you can get a decent sense of how this works from here. Basically, the upshot is each node's key is a prefix of its descendants' keys. So when you're looking for something in this tree, you know exactly how to traverse down the tree such that you find it, right? Because if you're looking for the word T, first you're going to look in the T spot, and then the E spot, and then the A spot. Okay, there's another different data structure called a Merkle tree, and this has the property that if you change any of the data in the tree, then the root hash changes. Because every node in the tree is, its hash comes from the hash of its children, right? So if we were to change, let's say, this piece of data, L1, that will cause there to be a different hash for this node. And if the hash of this node changes, then the hash of this node will change, which makes the hash of the root change. So, I mean, the thing that I want you to take away from this is that if you change anything at all in this tree, then the root hash changes. So the root hash acts as a fingerprint for the entire thing. Okay, there's this cool thing that you can do with Merkle trees called a Merkle proof. And what this allows you to do is prove the existence or non-existence of a piece of data in the tree. So suppose that you only know the hash of the root of this tree, and I want to prove to you that this node is in the tree. It doesn't have to be this one specifically because it's in the bottom left. It's just any node, right? I want to prove to you that this is in the tree given only that you know the root of it. So what we can do is I can actually just give you these blue nodes and the red node to prove that this red node is in the tree. I actually don't need any of the white nodes. So the way that I do this is I give you the root, right? I give you the root, and you know the hash of the root. So when I give you the root, you just hash it, and you check that the hash that you got was the hash that you expected, right? So you trust the root now. Now every node points to its child, so that gives us the hash of this node here, because every node points to its child. So we know every child hash of the root. Right, now I give you this node, and same thing, you can hash this node and check that the hash of this node is the one pointed to by the root node, and so on. So is this making sense by shake of heads? Okay, so response from the audience. Basically, the upshot is that I can't give you fake nodes to try to convince you that this is in the tree, because suppose that this red node was actually not in the tree, right? Or suppose that it had some different value in it. So if it had some different value in it, then this node's hash would be different, and the node above it that I give you will not have a child with the hash of the altered node, because the real node has a different hash. I'll keep going, and hopefully it'll stick with you. Yeah, we've got a question there. Just wait for them to bring the microphone over.
The question is, what's on the node? So is only the lower nodes bear some information, or all the nodes, intermediate nodes, also have information?
So I'll talk now specifically about this data structure that we're building at Ava Labs, which is why we're giving this talk. And every single node in that data structure looks like this. So every node has a key. It has a value, right? So both of these are just byte arrays. And then it has, in our case, it has an array of 16 children. And specifically, it has the hash of all of its children, right? So this is, like in this graphic, right? The node points to its child, and this is the way that it does that. Yeah, we have another question.
So in this like diagram, so whenever they're adding a new child, like as it's like transits down, is it the same as like a binary tree where it just appends it to it, and then everyone just has a copy of the child?
Yeah, so that's a good question. So the way that it works is that, so let's say that we have some node, right? And our node looks like this, right? And then let's say that we are adding a child to that node. Well, okay, first let's think, what does it mean to add a child in a radix trie? What it means is the child's key is a suffix of this node's key, right? Because by definition in a radix trie, every node's ancestors are a prefix of the node. So for example, if this key is the byte slice 1, 2, 3, then its child's key must start with 1, 2, 3. So it could be 1, 2, 3, 4, or it could be 1, 2, 3, 5, 9, or whatever. And the way that you decide which index the child is at, right? Because we have 16 slots here, but we don't necessarily have 16 children. So some of these slots could just be empty. So what you do is you look at the first byte that is different, the first one that is after the node's key. So in this example, let's say 1, 2, 3, and let's say that the child that we're adding is 1, 2, 3, 59 or something. So the way that you decide which slot to put it in is based on the first different byte. And specifically, in this case, we have 16 children. So if the first different byte is between 0 and 15, it goes in the first slot. If the first different byte is between 16 and 31, it goes in the second slot. 32 to whatever, and so on. So each of these is a 16-byte range, essentially. And that's how you determine which slot it goes in. Okay, and then when we're looking for something in the tree, we know exactly which way to traverse, because we know that if it is in the tree, then the next byte that we're looking for will be at a certain index, and that way we can traverse down. Okay, and then another thing that I want you to notice here is that all of the components in here contribute to the node's hash. So for example, if your first child, if its hash changes, then your own hash will change, and your parent's hash will change, and so on to the root. Okay, so imagine that each of these things has the child fields, but I just omitted that for clarity because the arrows kind of express that. So this is a Merkle Trie database, and the other stuff in here is kind of just a repeat. So now let's get to the cool stuff. So one thing that using this data structure allows you to do are these things called range proofs. And these are super cool, and these will let us do the syncing that we kind of started this with. So let's say that I want to prove to you that I'm giving you every key value pair in a certain range. So let's say, for instance, I give to you a bunch of key values, and I want to say to you, I can prove to you that there's no other key value pairs in the database in this range. And what do I mean by a range? I mean, let's say every key that starts with 0 to every key that starts with 32, right? I'm going to prove to you that there's no other keys in the database within that range that I am not giving to you. So how do you do this? So the person who is receiving the key value pairs, we assume that they have some trusted root hash, right? This is, again, the same way that you can get this as I described before. So what I do is I give you a proof, a Merkle proof of the first key value pair in the range, and I give you a proof of the last key value pair in the range. And then for all of the other key values, namely these gray ones, I actually don't give you the entire node, right? Like I'm not going to give you, I'm not going to say to you key 5's children are key 9 or whatever. I just give you the straight up key values. And it turns out that this is enough to prove that there's no other key value pairs in that range that I'm not giving you. Okay, and let's think about why that is. So let's say that I give you a Merkle proof for key 7, right? So now I have proven to you that key 7 and value 7 are in the database, and its parent, and so on. Right? And I've done the same for key 10 by these Merkle proofs. And let's suppose for a second that I'm trying to lie to you, and I'm trying to tell you that key 8 doesn't exist, right? So I just give you the start proof, the end proof, this node, and this node, but I omit this node. So what will happen is you put all of these nodes in the start and end proofs into a local copy of the trie, right? So you just start from an empty tree, and you put in all of the nodes that I've given you here, and then you put in these key value pairs. So what will happen is you will notice that the hash of this node, key 4, value 4, is wrong in your local copy. And the reason that you know it's wrong is because you have it from the node that I gave you in the Merkle proof for this, right? So you know that there should be a child here with some given hash, but in the local copy of the trie that you just made, it's not there. Okay? And then similarly, if I give you, let's say, an incorrect value here for this node, then you will not get the expected hash of the child here, right? Because this node that I gave you, this node that you trust and that you know is in the tree, says that there's a child with hash XYZ, but actually when you constructed the trie yourself, you got some other thing. Okay, and the same thing applies if I try to put in an extra key value pair, then its parent's hash will be wrong, and then that node's parent's hash will be wrong, et cetera, et cetera. I'm sure you have some questions about this, and we have plenty of time at the end to go through that. And then the final cool thing that you can do with these trees is you could do a change proof. So you might already know a bunch of key value pairs in a certain range, right? For example, you might already know all of the key value pairs where the keys start with between 0 and 16, let's say. But what could happen is if you're working with a system that's live as opposed to like a static file, right? Because like we said before, there's this approach that you could use with torrenting that doesn't work so well if the data is changing, and most torrents, I think really all torrents are static files, so this is not a thing that they have to worry about. But in the blockchain world, you know, people are changing the state all the time, so you need to be able to account for this. And the way that you do that is with these things called change proofs. And essentially the way that it works is that I say to you, I knew all of the key value pairs between, let's say, 0 and 16 when the root hash was this. And now I've learned that the root hash has changed because the database has changed. So I'd like you to tell me what's different in that range between those two root hashes, right? So I'm basically asking you for a diff between some snapshot of the database and some other snapshot of the database. And all you have to do is give me the same things as before, right? You give me a start proof for the smallest key, a Merkle proof for the largest key, and then you just tell me what changed in the middle. And by the same reasoning as with the range proof, you can just take your local copy of the trie, right, which is synced to some root hash, right? It's like one version of the database, essentially. You delete all the things that the peer tells you to delete, and you add all the things they tell you to add, and then you make sure that the root hash is what you expected. Whoops. So basically, this is the algorithm that you use with this Merkle database. You learn a recent root hash, and again, the way that you learn this is basically, in a blockchain network at least, you just ask a bunch of validators, hey, what's the latest database root hash? They all respond to you with whatever their answer is, and assuming that most of them are honest, let's say no more than 30% are dishonest, then if more than 70% give you the same answer, then you trust that, right? And now you have something to work with. And then basically you just ask a bunch of people to give you certain ranges of the database. So the first person you say, hey, can you please give me every key value pair between where the key starts between 0 and 8. You ask someone else for all the ones from 9 to 16, et cetera, et cetera. And then each time they give you a range proof, which proves to you that you've got all the key value pairs in a certain range. And then you keep doing this for the entire key range. And what you might find is that the database is updating, right? Because this is a blockchain and things are constantly changing. And if you notice that the root has changed, then basically you just ask for the diff between what you have and what you now know exists because the root has changed. And you keep doing that until you catch up to the root. And you use a change proof to get that diff. Okay, so now there's probably a bunch of questions, but before I get to that, you're probably wondering like, okay, is this a thing that exists, or is this like a hypothetical thing? Yes, it is a thing that exists. We are building our Merkle DB. It's inside the Avalanche Go repo in the X package because it's experimental right now. We are not like the inventors of this data structure. It exists and is already used for this purpose. It is just our own implementation and spin on it, kind of made for our purposes. And we intend to use this in all of, or at least additional blockchains. And this provides the benefit that it's really easy to state sync with this, right? So for example, on like the P chain on the Avalanche network right now, the way that you bootstrap and get up to the current state is you download every single block that ever happened, and then you execute them all in order. And that takes a little more time than we'd like. So with this, you can just download the current state of the P-Chain's database instead of downloading the entire history and creating it by executing every state transition that ever happened. So with that, I will answer some questions, and I think we have 5 minutes.
Okay, thank you. Congratulations for the talk, thank you. In slide 12, where you showed the range proof, so I get the pink path, I get the blue path, and I get a set of nodes. How do I know how those are structured? I mean, where the position of each one is? I do by the index, by the key.
Yeah, that's a good question. So the way that you determine where a given node goes, or really to say a given key value pair, like how does this key value pair map to the tree structure? The way that you do that is you follow along the child hash, right? So the root has no key, let's say, right? So let's say that the first, let's say that there's a key value pair in the tree where the key is 1, right? So the way that you would find that in the tree and the place that you would insert it into the tree if it doesn't already exist is you would put it at the child 1 position, right? Because like the first difference from the parent, if the first difference is between 0 and 15, it goes in this position. If the first byte difference is between 16 and 31, it goes in this position, and so on. So basically, just the key itself tells you where in the tree it should go.
Thank you.
So on this note, whenever you have let's just say, yeah, the root has like no key at all. I'm just only thinking in terms of like, a binary tree with like left and right branches. Can you go back to like slide 12, I think it was? Yeah. So with that same like logic, would anyone like the red ever know about its siblings on the right branch, or it only cares about the one that's on the like left side?
So are you asking whether...
Like for instance, there's like key 7 have all the hatches for what's on the right, where it's like key 3, 6, and 13, where they exist, or that doesn't matter for this instance?
They are not ancestors of these nodes, so their hashes are unaffected by these, because the hash of a node is only affected by its descendants. So if any descendant changes at all, or is added or removed, then all of the ancestors, up to and including the root, change, but things that aren't an ancestor don't change. Okay, we got a couple more minutes, so...
Hey, thank you for the talk. I have a question. You mentioned that you will be using this for downloading the state, the final state of a chain. What about the blocks, actually? So you are planning to not download the blocks and execute them again, but just downloading the final state. But are you planning to download the blocks afterwards or something?
That would be a separate thing from this. It's not strictly necessary for a client running Avalanche or just a blockchain in general to have the full history. So a node with the full block history would be called an archival node. And that doesn't necessarily need to be inside of Avalanche Go. So what we could do is potentially have like a separate mode of operation that does support having every single block in the entire history, but it is not like a must-have. And that would not be done as part of syncing a Merkle DB. That would have to be like a separate thing that a client chooses to do. Got one more? Anyone? Cool. All right, well, I'll hang out after if people are shy and have more questions. Thanks.